Good afternoon, Professor.
Good afternoon. Good afternoon. Oh, I just
Good
lost my.
afternoon,
Good
Professor.
afternoon. Good afternoon, Caroline. Good afternoon, Savannah. I think. Good afternoon, Kevin. Okay, wait. I just lost my board again. Good afternoon, Kevin. Good afternoon, Caitlin. Good afternoon, Erini. Good afternoon, Amanda. Good afternoon, Estrella. Good afternoon, Erica. Good afternoon, Stephen. Good afternoon, Amy. Good afternoon, Jose. Good afternoon, Adon. Good afternoon, Samaya. Oh, that was fast. All right, that's awesome. I said Carol. Did I say Caroline? I'm sorry. Good afternoon, Caroline. Yeah, I did. Okay. Okay. Good afternoon, Caroline. And I think that was Savannah. Okay, and we're gonna get going right away. Even though I keep losing my board. We are okay. All right, hang on 1 second. Okay, someone else is here. We're gonna do something a little bit. We're gonna try something slightly. I'm gonna do something in the name of efficiency. We're gonna. Okay, well, hold on. Hold on. Other people. Good afternoon, Rashmahan. Awesome. All right, wait. Other people are here. Okay. Bear with me for one more second. I'm sorry. Okay. Oh, that's odd. Hold on a minute. Okay. I'm going to try a different approach today just to see. Okay. I'm going to ask you guys. Oh, wait, someone else in the chat. Oh, good afternoon. Good afternoon, Douglas. Good afternoon, Rashma. And Sumaya, if I didn't say. Okay. I want to try something slightly different. I don't know. We'll see if it works. How can I say this? Okay. You'll see on the notes, right? You see on the screen right here. What we've been trying to do, what's happening in the math methods homework. Wait, sorry, I have all these speeches to give, but I'm trying not to give a speech. Yes, all right, look. We are trying to solve a certain differential equation. The differential equation is here in the middle of this page. All of our math work right now and the math methods homework that you're all in the middle of, that I've gotten some really fine drafts of, and I'm going to get more from you. And some people have a ton of points and are going to get the remaining points very soon. And many of you are going to get all the points very soon, blah, blah, blah. It'll get more and more clear as we're going through it. But all of this math that we're looking at in the math methods homework number 2 is an attempt to get enough calculus back under our belt to be able to understand, appreciate, and solve or solve this differential equation that's right in the middle of the page here. The differential equation got motivated by physics, but now it requires math to unpack. Okay. Differential equations are puzzle solving. They are not straight up algorithmic procedural straight line paths. What I'm saying, and that's no matter how advanced a person is in math or physics, a differential equation is something that you solve by trying and by knowing various techniques that have had various levels of success in your past experience. And if you're a scientist, being also informed by things that you see and measure in the lab. So this differential equation we're trying to solve it means that we're looking for x as a function of t. We're looking to be able to predict where a mass on a spring is at a given moment of time, right? Given this information that we have about the rate of change of the mass's position as a function of time. Okay, so we're trying to solve this. Now, what I've been saying, but it's not easy. And we have to sort of go through it like from different perspectives over and over again, because it's not a straight line path. What I've been trying to say in class and what you may have sort of been seeing indirectly in the lab is that the way to solve, one way to solve a differential equation is by conjecture and verify, i.e. guess and check. It's a very experimental way of solving an equation. There are not necessarily more direct ways to, well, there aren't more direct ways to solve a differential equation of this fashion. We have to, at some level, guess and check, or at some level do trial and error. Now, many of the math questions in the math methods homework, many of the early questions in the math methods homework basically present you with a guess and then ask you to test that guess and see whether your guess does or does not solve or satisfy a given differential equation. It's trying to give you practice in testing a guess and in understanding what it would mean to know whether the guess worked or not. Both of those things are already a skill. To test a guess means to take a derivative or two derivatives, often for us two derivatives, because the differential equation that we're dealing with is a second derivative equation. So anyway, in the math homework that hopefully you'll get increasingly comfortable with as you see an increasing number of lectures on this, you're being asked to take derivatives and see whether what you get is what you're trying to get or not. And some of you are getting better at that, and some of you need more practice at that. But what I want to do today is go in the other direction and get at the issue of where do we get our guesses from in the first place? We have to get them from somewhere. There's not a direct fashion for building a guess. If there were a direct formula for building a guess, then it wouldn't be a guess. Like it is a guess, a conjecture, an educated guess that we're building. And here in the homework, at least in the early exercises, you're sort of given the guesses and you're trying them out. It's pretty important for us to look from the other perspective, like where did this guess come from in the first place? Okay. So there goes my board. Hold on a second. Okay. What I'm saying, so our guess, the thing that we are guessing as an, like, remember, we're looking for the differential equation is the one right here. That's the equation. The second derivative of x with respect to t equals negative k over m times x. That's an equation. That doesn't tell us what x is. It tells us about the nature of x's second derivative. And puzzlingly, it states that the second derivative of x with respect to time is some function not of time, but of x itself. It's a circle. That's what the fact that the right-hand side of that equation has an X in it rather than a T is literally what makes that thing a meaningful and challenging differential equation. What we're looking for, again, I'm just saying again, what we're looking for, what it would mean to solve it would be to get some function of T, some expression for X as a function of T that actually satisfies that condition. We want some X such that when we take two time derivatives of it, we get back itself times K over M times a negative sign. Okay, that's what we're looking for. Now, what we guessed, what it turns out we guessed, and what you're playing around with in the homework assignment is we're guessing some kind of cosine function. Now, it turns out that's a good guess, but where did I get that guess from? Where did cosines come into our lives? Well, partly because we're scientists and we've been working in the lab. If you think about, so I'm on this, yeah, I'm saying that if you think about, if you just actually track a mass going back and forth on a spring in the lab, and you track where it is for every given minute of time or second of time or millisecond of time or whatever, if you ask, where is it, wherever, for equal intervals of time, you'll notice that the mass goes back and forth in a smooth, somewhat simple way. It doesn't start at zero. It starts at some position that we call x naught. If it started at zero at equilibrium, it wouldn't go anywhere. But it starts at some displacement from zero. So on the y-intercept, the very first point on this graph is 0, x naught. Like at time equals 0, I think it says it somewhere. It says on the next page. At time equals 0, x equals x naught. Well, and then from x naught, the mass starts proceeding in towards x equals 0, and it hits there, and it goes past there all the way to x equals negative x naught, and then it turns around and comes back again. So it goes back and forth and back and forth and back and forth. So if I just picture the graph of the data that I would get from the lab, I would picture something that's going back and forth and back and forth. Either I literally got that data or I'm picturing it in my head. I recognize that back and forth graph, or at least the simplest, smoothest version of that back and forth graph, I recognize from math classes as a cosine graph. Even if I never walked into a lab, I would think the graph would be this smooth, simple back and forth curve that we know as cosine, because anything simpler would be too simple. Like if I guessed straight back and forth, that doesn't make any sense, because then I'd be guessing that the thing goes at constant velocity in one direction, and then instantaneously, like in no time at all of a sudden changes its velocity to the same speed, but in the opposite direction. In other words, in no time at all, I'd be guessing that in no time at all, the object slows all the way down to 0, turns around and speeds all the way up to the other velocity and continues going. That makes no sense. In other words, the simplest possible graph picture of an object going back and forth continuously forever would be a curvy graph, not a straight line graph, a curvy graph, where not only are the values going back and forth, but the derivatives, the rates of change are going back and forth, and the rates of change of that are going back and forth, et cetera, et cetera. This is what we know as a cosine graph. First of all, if I knew nothing else about the cosine graph, I would guess it for that experimental laboratory reason. But then also, if you know anything, if you remember from calculus classes in math, the cosine is a function whose derivative, we talked about this last time, its derivative is negative sine. The derivative of negative sine is negative cosine. The derivative of negative cosine is sine, and the derivative of sine is back to cosine. In other words, you can take derivatives of cosine forever and never get to 0, always get another trigonometric function. So what? So that implies that this is the kind of function that we're looking for, the kind that has not only a position that is smoothly changing, but a velocity that's smoothly changing, an acceleration that's smoothly changing, a jerk that's smoothly changing, et cetera, just like we found in questions 6, 7, 8, and 8, right? It has the right properties. Finally, remember the differential equation that we're looking at says we want an equation for x such that the second derivative of x, d2x dt squared, equals a negative times a constant times x itself. Well, the derivative of cosine is negative sine. The derivative of negative sine is negative cosine. That sounds pretty good. Cosine, if you differentiate it once, if you differentiate it twice, you get back negative cosine. If we were to take the cosine of something and use chain rule, then when you differentiate that twice, you'll get negative something times cosine. That sounds like a really, really good guess. None of what I just said proves anything. None of what I said proves that cosine is the right answer. Actually, we proved that cosine was the right answer when we took two derivatives of it last week and showed that it was the right answer. And we're going to do that again. But right now, I'm not interested in that. Right now, I'm trying to show you where did I get my guess from in the first place. I'm guessing cosine of some kind because of all the things I just said. Because of, I could picture the experimental data, and because I know that the nature of cosine is to be differentiable in the right fashion, that I take two derivatives of it and I get it back itself times a negative sign. That's why I guess cosine, okay? But then, and I said I was gonna do something unusual today. I'm just about to, but this is why I guess cosine, okay? Then I go one step further and I say, okay, I guess some kind of cosine. I can't literally just guess x equals cosine of t. And again, for those of you who are losing sight of what I'm talking about, which is very possible, well, I keep saying guess this. What am I guessing? Remember, I'm trying to guess some kind of x function of t that satisfies our differential equation. I'm trying to figure out how x depends on t such that Hooke's law is actually obeyed. I'm trying to figure out what the position is doing in time such that the acceleration is a constant function of position, okay? So I don't just guess, so I'm already arguing, that x is some kind of function of t, but I can't just say x equals cosine of t. I'm gonna leave blanks. I'm guessing here on this page, I'm saying x equals blank cosine of blank times t, like, just put, yeah, why? Well, first of all, again, if you sort of follow what I just said about chain rule, why am I putting in blanks? Partly I'm putting in a blank before the t because of the argument I just made with chain rule, that if we want our answer to be, if we want our second derivative to be negative times k over m times x, then there better be something that multiplies our whole cosine. There better be something that comes out of our derivatives due to chain rule to get that k over m on the outside of our answer. But even if you don't like calculus, you don't like that yet, the reason that I've got to put blanks in my expression is I'm a scientist. I believe all this stuff relates to measurements that I'm making in the lab and units of measurement that work out consistently. Well, you can't take the cosine of a second. Like, I can't take the cosine of time. I literally cannot take the cosine of a second. I had to take the cosine of something called a radian, right? Like literally, I mean, or degrees if you want to be really primitive, but if you want to be actually direct and sophisticated and rigorous and proper, you cannot take the cosine of a second, but you can and must take the cosine of a radian. So my first argument is there's going to be some kind of constant multiplying that by that t, some kind of constant before the t that has the appropriate units, radians per second, so that the per seconds cancel out with the seconds in time, and I'm left with radians. Like there must be something there. I don't know, what its value is, but it's got to have some unchanging value that's measured in radians per second, so that then it gets multiplied by something measured in seconds. We're left with radians, and we can take the cosine of it, right? So that's the first thing. There's got to be something there, and I could call it anything. You could call it A, you could call it B, you call it C for constant, but traditionally physicists call it lowercase omega, a letter that looks like W but is actually the lowercase Greek letter omega. traditionally, that's what we call that thing that we're going to put next to the t. I don't know much about it yet. I just know it's right now my omega letter is like a placeholder. I'm just saying something is going to be multiplied by t if I'm going to take the cosine of it, something that's multiplied in radians per second. Similarly, on the outside next to the cosine, I got to put something, some constant, because the output of cosine just ranges between -1 and 1, the pure numbers, -1 and 1, right? The biggest cosine ever spits out is the pure number 1. In fact, very specifically, when t equals 0, as it says on the sheet, when t equals 0, the cosine of omega times t will be 1, because I don't care what omega is. Omega times 0 is 0. The cosine of 0 is 1. So when t equals 1, cosine will spit out, I'm sorry. When t equals 0, at the beginning of this experiment, cosine will spit out 1. And if I don't multiply that by something, then that implies that x at t equals 0, that would imply that x equals the pure number 1. That makes no sense. First of all, x has to be measured in meters. I've got to multiply this whole thing by something that's in meters in order for my ultimate output of this function to be in meters. But second of all, there was never any rule that the farthest that x could ever be from equilibrium was 1, even 1 meter. We know that in the case of, for example, of homework 1, of homework 1, question 9, our mass started at a position of 0.15 meters, 0.15 meters from the equilibrium. That was its initial displacement, x naught, measured in meters, and it also turned out to be its maximum displacement from 0, what we call the amplitude. Like we found out in questions 6, 7, and 8 of homework 1 that our mass oscillated between the values 0.15 meters and -0.15 meters, right? It went from 0.15 all the way through 0, all the way into the negatives, into -0.15, and then back and forth and back and forth. So we don't want a function that just goes back and forth between 1 and -1, the pure numbers. We want a function that goes back and forth between 0.15 meters and -0.15 meters, or whatever x naught initially was. So if we just multiply the whole cosine expression by x naught, then we'll have just that, right? By multiplying the whole thing. In other words, I'm saying there's got to be some constant next to the t. That's got to be measured in radians per second. I don't know much about it yet, but I know it's got to be measured in radians per second. I'm just going to call it omega. Then there's got to be a constant outside the cosine. It's got to be measured in meters. And in fact, this one, I could just give a new name if I wanted. I could call it Fred, I could call it B, but I actually know a lot about it already. What I know is I know that value outside the cosine is not just any value measured in meters. It's got to be the initial and or maximum displacement of the object from equilibrium. Right? Because it's got to be the biggest value. It's got to be the value that x takes on when t equals 0. So literally that value there is going to be x naught, okay? And the value inside, for my guess, now I'm arguing vehemently here. I'm really trying to argue why this guess makes a ton of sense. If I argue well enough, hopefully you almost think that the guess is right. Now, it does turn out the guess is right, but you only have to believe what I'm saying enough to see why this is how I came up with the guess. This doesn't prove it. But this is where the thinking is, that we start with a cosine shape, and then we leave room for two constants to adjust the units, and to adjust to units and to whatever we know about the initial conditions of this phenomenon. I mean, and this is how people solve differential equations. They first conjecture the basic shape of the solution, and then they conjecture the details of the shape based on units of measurement and initial conditions. So what I have now, okay, is a guess. My guess for how x varies as a function of t for something that's oscillating back and forth under the influence of Hooke's law, my guess is x equals x naught cosine omega t. X naught you could also call A. It's measured in meters. Omega is this new thing, is this new placeholder value that I'm putting there, that all I know about it right now at this moment is that it's measured in radians per second. Okay, omega's got to be measured in radians per second. Now, here's where I'm going to pause. I'm going to do something a little bit new. But and by the way, again, if you're track, all of what I'm explaining here is it's hopefully ultimately helpful to homework 2. It's not a particular exercise on homework 2 yet. If you're just tuning in, like I'll go back to the actual problems going over my promise on Wednesday, but I'm just trying to explain something right now. If anything, everything I'm saying right now is ultimately related to question 9 on homework 1 for what it's worth. But it's all this big topic of solving for x as a function of t when we know that f equals negative kx. Like that's what's going on here. So my guess right now is x equals x naught cosine of omega t. I'm claiming that we know what x naught is. It's the initial position, the initial displacement from equilibrium. And I'm claiming that we don't know much about omega, but that omega is some constant number that must be measured in radians per second. Now, I need to explain what we need to understand what we're going to test this guess. I haven't tested it yet. I haven't proven it, but it's my guess. And it is going to, it is. Yes, it's exactly what it is. Yes. Good. Hold on. Someone just said in the chat, it's like x equals a cosine omega t. Yes. Good. If you're recognizing this from the homework too, yes, this is exactly x equals a cosine omega t. That's good, direct chat person. And I am saying x naught and a are 2 names for the same thing. We call it x naught when we mean the very first displacement from equilibrium. We call it a when we're implying amplitude, i.e. maximum displacement from equilibrium. And I'm saying that for an oscillator, they are one and the same thing. Wherever you start, if you start from 0, is the farthest you're ever going to get. So yes, this is exactly the expression from the homework, right? But the one term that's sort of new that also you're dealing with a lot in the lab, I know it keeps coming up in the lab, is this omega term. So now I want to stop. I want us to, before I even test this guess, I want us to understand what might be meant by omega. Don't be intimidated that it's a Greek letter. I mean, it's just a Greek letter. It could have been any letter. It's just a name right now. But yes, it's a name for something. I want us to understand what it's a name for. It's a name for some kind of rate of radians per second. It's some sort of rate at which the mass on the spring is undergoing radians per second. But that's worth explaining and making sense out of, because it does raise some confusion and some questions. People often get confused about omega. People get stuck on omega. And anybody who allows themselves actively to admit that they're confused about omega usually can straighten it out, like with my help, with the help of what we're about to say. But if you don't admit to yourself that, if you just try to memorize omega or just skip past it, the confusion will always be there and you'll be a wall that you will have a very hard time getting through. I want to admit right now that there's something confusing about omega. A, it's a Greek letter, but B, what's confusing is it's a measurement of some kind of radians per second. And we're talking about something going straight back and forth in a straight line on an x-axis on a spring. So what you might be half consciously wondering or consciously wondering, you might be wondering the thing that I was eventually wondering when I was a confused student or even when I was a confused teacher is, wait a second, this thing is going back and forth. Like, what do radians have anything to do with something going back and forth? Like, as far as I remembered, radians, they had something to do with cosines, yeah, but they had something to do with angles or something. And where are the angles in this? What angles are we talking about? And then when I thought about it, I was like, I know radians have something to do with angles, but I was never really that comfortable with what they had to do with angles. Like, I memorized angle measurements in radians, but I always converted back to degrees. Like, I did it when I had to, but I never really understood what the heck radians had to do with angles. And I certainly don't see what angles have to do with this thing going back and forth like this. If any of those questions occur to you, you're in the right place. I'm here to answer them. The rest of this discussion today, the rest of this class today is to try to unpack exactly what I mean by radians per second. That omega term is ultimately called angular frequency. It's measuring some rate at which we're traveling through angles measured in radians. That is what it is. It's a rate of going through radians. But what that has to do with something going back and forth is a very important, real question. What I'm going to do today is a slight experiment. Because this is so important, instead of me just yelling and yelling about it for the next 45 minutes, because I know with something like this, for some people, I'm going to go too fast and yell too loud. And for other people, it's going to seem like I'm going too slow. You're going to feel like I'm explaining concepts that some of you will feel like you knew in 10th grade, whether you did or did not. So as a slight, what I'm going to do is ask you, you'll notice that the notes for this class, like the whiteboard thing here, the PDF, it has 7 more pages to it. I've already dropped it into your, or dropped it, whatever, uploaded it into your Google Classroom. I'm going to ask you, first of all, can you raise your electronic hand if you see the PDF, class notes 10 or class notes 11? I can't, it's one, whatever the most recent class. So Caroline, thank you. So you see it. That means you see it. Great, great. And Caitlin and Amanda, thank you so much. And Mackenzie, Irini, Erica, Kate, Katya, Kevin, Jose, Amy, awesome. Savannah, thank you. Amanda, who else did I miss? But thank you. Awesome. All right, so you see it. Good. So I'm going to ask you now, for good or for bad. I'm going to shut up. I'm going to ask you to read through that. And Jose, thank you very much. Unless you're asking a question. Okay. Right now, you guys, read it to yourself at your pace. Okay. It's going to clarify things for some people. It's going to, well, hopefully it's going to clarify for everybody, but just read it at your own pace now for like 10 minutes. And then we're going to see. And I'm going to ask you questions about it, like I am in the chat and stuff. I'm going to ask you, but this will either be more efficient or less efficient, but just read the notes right now and see. And what you're really looking to figure out in reading those notes is, first of all, what do radians have to do with cycles? Excuse me. What do radians? Well, yeah. What do radians have to do with oscillations? And ultimately, you want to know what angular frequency omega is actually measuring in terms of something going back and forth. So please read. I'm going to shut up. I'm going to turn off my, well, no, I'm going to be here. I'm here. I'm going to mute myself. Sorry, I was muted. I didn't realize. Okay, sorry, I was muted. Sorry, someone told me that I didn't realize I was muted that whole time. I was trying to fix it. Right. Someone pointed out that they couldn't see the slides, just the post. So I was spending the whole time trying to fix it because they were right. It wasn't visible there. But now, and I was muted and I didn't realize it. If you check now, it should be class note 11 and it should be there and the material should be there. And please let me know. Okay, great. Thank you very much, direct chat person. Great. So it's there now. So please, and you could start on page 6. Like we've just gone through the first. Okay, thank you. Yeah, so start at page 6, but take your time. I mean, I'm not going anywhere, but just take your time. And write down if you have any. The first thing I'm going to ask you when you get back is, do you have any questions on it? So, okay. Okay, you see it. Good, good. I'm glad you see it. Okay. Sorry about that. So I'm gonna ask a couple of questions when we're done with this. Well, I'm gonna ask you if you have any questions first, then I'm gonna ask you some exercises like in the chat. I think it'll be helpful and important. So we're not done with class or anything. We have 27 minutes. So I'm going to ask you again that when you're done reading, and it's not a test or anything. I mean, I'm not trying to make anybody nervous, but I do want to see if you can sort of get this from this reading or this pack. So when you think you're done with the reading, when you think you get the basic idea, like when you think you know, the real thing is when you think you know what a radian is and what it has anything to do with a mass going back and forth on a spring, then I want you to put up your electronic hands when you think you're done. If no one does that at all in like the next 8 minutes, I'm still probably going to cut things off. So, but please put up your electronic hand when you're comfortably done. I'm not trying to rush you. We still could take another like 8 minutes or something. But when you're done, please raise your electronic hand. Awesome. All right. I'm seeing a lot of hands. That's great. I'm still giving I appreciate that I'm seeing a lot of hands. I understand that I don't see all the hands. That's great. I'm going to wait a couple more minutes, but please be aware. I hope. Okay, cool. I'm going to give you like 2 more minutes, but I totally appreciate the hands that I see. I'm going to update the thing that's in the post because we're going to go straight. Wait, am I? No, I won't. Okay. I'm going to give you like, even if you're not, well, actually, I also know it's always possible. I mean, someone's just facing it. I'm going to say this because I now see a lot of hands and I'm not, and God, I'm so sensitive to this. Remember, I have children of my, I know everybody does this at different paces and it's impossible on Zoom. And we all have to do a balancing act. But so what I'm trying to say is in the direct chat right now, just tell me if you'd like me to shut up and you'd like to take like 2 more minutes and it'll make a difference to you. I totally will. If like 2 more minutes of quiet will make a difference, I'd rather do that. So put in the direct chat if you'd like a little bit more thought time. Okay, wow. Sorry. Okay. If you need more time, tell me in the direct chat, but no one is saying that yet, but someone is putting someone has put a question in the direct chat that's so perfect. It totally makes me feel like this was a worthy undertaking. I'm not going to call anybody by name, but I want to say there's one thing in the direct chat. So if you put some, and I'm going to read the question. I'm not reading the name. It's a great question. The question is, when is angular frequency useful and when is standard frequency useful? What is the benefit of having both? Okay, that is a perfect question. If you're the one that wrote that question, please submit it for points in the class participation thing. And if you're someone else and you're thinking that question, you're totally with me. And it's not too late to ask other questions like that. Okay, that really shows that someone has done the reading. That's exactly the right question and it's one of many. I'm not saying it's the only one. I'm not saying that's the only cool person on planet Earth, but I am excited because I feel like education's happening. Okay, and I'm going to answer that, I think. So, okay, I'm going to I'll try to answer that first. The answer might make even more sense, like once we go through a couple exercises. But okay, to everybody, I'll try to work backwards on this. She or he is absolutely right that I'm trying to explain this thing called angular frequency, omega. And by the way, don't forget, why am I explaining it? Because I'm assuming there's got to be this omega in my cosine guess. Like I'm saying, even before we solve this differential equation, even before we proved anything, if we're trying to guess what might solve it, if we're trying to guess an equation, a function that would tell us how to predict where a mass is as a function of what time it is. Like if we want an input-output rule for you name the time, I can name the place, right? I'm saying, the whole point of this whole discussion is I'm saying that my first guess is going to be something like x equals x naught times cosine of omega t, where omega is this new thing called angular frequency that I'm just like guessing there before, like we've ever talked about it before, or before we've proven it. So then the discussion that you just read in the pages is ultimately trying to explain what angular frequency is, and it ultimately tries to relate it to regular everyday standard frequency, thinking that you might have a better idea of what that is. So it's trying to relate it to that. So at least one person's definitely doing the reading correctly. But the person is, so what I ultimately want to say is, yes, angular frequency is simply 2 pi times standard frequency. If you know one, then you know the other. And if you know the other, then you automatically know the one. That is true. And if you understand one, then you can understand the other. So the person who's asking this is totally with me, but then they're saying, well, why do we need both? Great question. Great question. In order to answer that, let me go on one more beat and just say, especially assuming people sort of did understand. Oh, and you can put your hands down now too. I'm sorry. You can put your hands down now. But thank you. Yeah, I'm going to go one step further and say, actually, what the well, I'm going to try to put up my board here. Yeah, let me try to put up the board. I'm actually trying to say ultimately that there are three quantities that are intimately related. Three quantities, three different ways to describe something cycling back and forth and back and forth. There's three different ways to describe something or to measure the rate at which something cycles back and forth and back and forth. One way is angular frequency, the new concept that I'm trying to explain. Another way is standard frequency, just the number of one way is angular frequency, which is number of radians per second. Another way, the more old-fashioned or conventional or common or like sensible maybe way, is standard frequency, number of cycles per second. Like how many round trips did that mass make per every second, right? That would be standard frequency. And actually, if you're doing the reading, there's a third way, which is period, which is number of seconds per cycle, right? So I'm saying, and I'm trying to put this up on the board in 1 second. Hold on. I'm saying that if you want to talk about the rate at which something oscillates back and forth, even or especially if it's in a straight line, even if it's in a straight line, like a mass is going back and forth in a straight line, it's oscillating over and over again. It's making these cycles. I am absolutely saying to the direct chat person and everybody, I'm saying there's three fully equivalent ways to capture that same information. Sorry, some of the hands are still. Oh, and if the hands are up because you have questions, I'll totally try to get to those too in a minute. But if not, you can put. Oh, am I sharing the board? No, I'm trying to put up the board right now. Sorry, I'm trying to get it. Here it goes. Here it goes. Thank you for asking. Here. Here. Okay, here comes the board. No, also a good question. Oh, and Shumai, is that a question, Shumai, or are you just keeping your hand up from? If it's a question, give me 1 second. I'll totally try to answer it. But here, let me say. Yeah. So now I've got this thing on the. Yes, I am literally trying to say that. Thank you, Shumai. Sorry, I am saying that there's three different things that are you can measure. You can measure the number of seconds per one cycle, and we call that period, capital T. You could flip that and measure the number of cycles per 1 second, so that if something takes 4 seconds to do a cycle, that's called its period, 4 seconds per cycle. You could flip that. I mean, literally, you could take the inverse of it and say, oh, if it's taking 4 seconds to do a cycle, then it does 1/4 of a cycle every second, right? So you could talk in terms of period, seconds per cycle, or you could talk in terms of standard frequency, cycles per second. And indeed, sidebar, the actual name for a cycle per second is called a hertz. Okay, from now on, 1 hertz, it's a name, so it sounds like it's plural, but it's not. 1 hertz is 1 cycle per second. So we could talk in terms of period, we could talk about frequency, or we could talk about angular frequency, which would be radians per second. And the conversion factor there is just that there are 2 pi radians for every cycle, which is what you just read about, right? There's 2 pi radians in every cycle. So now to finally get to the direct chat person's question, it's such a great question. I'm using it as an excuse to summarize a little bit first. But so she or he is right that I'm actually literally saying that there's 3 different ways to describe the same measurement, which is rate of cycling, rate of oscillation. And if you know any one of them, you automatically can get the other 2. You can convert back and forth among them as per this board right here. Okay. If you know one, you can get the other 2. If you understand one, hopefully you can ultimately understand the other 2. They're all 3 different ways of saying the same thing. They're all interrelated. But yeah, okay. So the great question someone's asking in chat is, well, okay, I get that, I guess. I mean, okay, fine. I can see how to get from one to the other. But then if that's true, if it's that tight of a link, why the heck do we need all 3? Fantastic question. And here's the answer. Okay. I mean, she or he asked, like, why do we need 2? I'm saying there's actually 3. So why do we need 3? Great question. Because period, okay, and hopefully this will help everybody understand why we're having this whole discussion and everything. Period, to all of us at any level of math or physics, period, to all of us is the easiest one to picture, the easiest one to relate to, the easiest one to talk about or visualize, because, I mean, maybe not everybody in the world, but generally speaking, it's the most direct way to picture oscillation because it, period, seconds per cycle, is the one that is most directly measurable in the lab. Like your first lab of the semester, I believe, or your second lab, or both, you were doing all this work where you were measuring what's the amount of time it takes for something to do a round trip or 20 round trips or whatever. And everybody could do, you just start your stopwatch when the thing is at amplitude position. It starts going, it makes 20 full cycles. You stop your stopwatch when it's back at amplitude position, and you get a number of seconds and you divide by 20. And that's not like the stupid thing to do. That's like the smart, reliable, low error thing to do. So period is the most experimentally fundamental measurement, and therefore the easiest one for us all to picture and know what we're talking about, number of seconds per cycle, right? On the other end of the spectrum is angular frequency, which is really hard to measure in the lab. Like, how do you measure pi, radians, what? And it's very hard for people to picture angular frequency. Not just you, like I'm teaching it to you guys because I know it's new to you, but I know what angular frequency is. I know what angular frequency is, but I still have to translate in my mind back to period of frequency. Angular frequency is the hardest to relate to at first, the hardest to picture, certainly the hardest to measure, but we need angular frequency. And the reason we're having this whole discussion today, we need omega, we need something measured in radians per second, because this whole function that we're getting, this back and forth function, this back and forth motion in linear space is best described with cosines, and cosines only apply to radians. How did that happen? Why is that happen? Or put another way, well, yes, this back and forth motion is best described with cosines. Cosines only apply to radians. Why do cosines and radians have to do with this? Because, and this is the point of the reading, a radian is ultimately a measurement of angle. Angle is not the intersection of two lines. Like, if there's any big lesson of all of today, is from here on in, when you think of angles and you think of radian measurement and you think of taking cosines and stuff, don't think of just two lines intersecting. Think of an angle. What an angle is a portion of a circle, a fraction of a circle. A right angle is a quarter of a circle. No matter how big my arms are, no matter how big the circle is, or right, a right angle, everybody in the world knows it's a quarter of a circle. Or a 360, my 8-year-old son knows. He always goes around going 360 no scope, 360 no scope. He knows what a 360 no scope is. I don't freaking know what a no scope is. I mean, I think it's like some gun in Fortnite or something, but he knows what a 360 is. What does he know? But he doesn't know anything about radians or this or that. And he doesn't know why there's 360 degrees in a circle, and neither do most of us. What he knows is a 360 is a full circle. So he knows just enough math to then know a 180 is a half circle. He knows that. He doesn't know trig, but he just recognizes full circle, half circle. That's what angles are. 90 degrees, quarter of a circle. Now, what I'm saying in the reading is 360 and 180, 90, you're used to those numbers because you've been hearing about them since you were little kids. They don't actually make sense. They just feel like they make sense because you've been hearing them forever. There's no sense that you're using as to why we ever divided a circle into 360 degrees. But a circle can be divided into 2 pi radians. Now that sounds like it doesn't make sense because it's like a Greek letter, and the letter pi stands for this number that's infinitely non-repeating, blah, 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 blah. Forget all that. Pi is just a number. Pi is a number and it's close to 3. When we say that from here on in, when we say that 2 pi radians is a full circle, right? We mean just that. We mean 2 pi from now on is what you think of as a 360. A pi is a 180. 2 pi radians is a full circle. Therefore, approximately 6 radians. 6 radians. Remember, pi is just a number. Pi doesn't have units or anything. It's just a number. So when we say 2 pi radians, we're saying about 6 radians, because pi is about 3. 6 radians is a full circle, just like saying 360 degrees is a full circle. You might think 360 makes more sense. I submit to you, you just think that because you're used to it. I'll tell you, if we have time, I'll tell you where the 360 came from. It didn't come from any place that makes any sense that we're thinking about when we're doing geometry. A 2 pi radian is a full circle. And we could take and a pi radian is a half a circle. Pi over 2 radians is a quarter circle. And here to finally, to go back to answer the direct chat person's question, here's the deal. We have a mathematics of circles. We have all these functions, cosines and sines, that apply to portions of circles known as radians. And the whole reason that all of it works, the reason we can say that circles are always 2 pi radians in angle is the fact that no matter how big a circle is, the ratio of its circumference to its radius is always the same. The magic of the pi number is not the craziness of the number, it's the fact that it's a number at all. The fact that any tree you pick, if you take a string and you wind it around the tree and you put that string down on the ground, and then you cut across the tree and put a string across the tree and put that string down and just compare the diameter string to the circumference string, the fact that the circumference string, the fact that you can always fit a little bit more than 3 of the diameter strings into the circumference string, no matter how big the diameter or the circumference is, no matter how big the tree is, the ratio of going around per going in is always the same. That's what we mean by pi, okay? And that's what we mean by radians. It's just that ratio. So what I'm saying from now on, sorry, I'm getting too, but that question was so great. I was going to do an exercise with you, but just that question was so great. And I probably lost the person who asked because I'm like going off on this whole thing. But here's what I'm saying is that circles have this property that it doesn't matter how big they are, we can still take functions of circles. We can still do cosines and sines and angles. An angle is a chunk of a circle that is universal regardless of how big the circle is. So we have this math of circles, circle functions called cosines and sines and all that. What we're going to do is take the advantage of the mathematics of circles and graft that on to the physics of cycles. The whole point is that what we know about cycles, regardless of how wide or big in space a cycle is, because we use the mathematics of circles. So long, short story long, I'm saying angular frequency is what we need in order to take cosines and make predictions and do precise quantitative math on this phenomenon. To actually make a prediction of where something's going to be when, we need to use radians. We need to use angular frequency in radians so that we can take cosines, so we can plug in and actually get a prediction. So the radians, the angular frequency, are the most mathematically direct and powerful. But the period, so radians per second is the most mathematically direct and most mathematically powerful. Seconds per cycle is the easiest to picture and the easiest to measure in the lab. Standard frequency is the bridge between the two. Okay, what I can picture is period. What I need mathematically is angular frequency. So the bridge between the two is standard frequency. I'm going to say that one more time because it was such a great question, but I'm going to say it backwards. What we need mathematically is angular frequency, so we can take cosines. But what we can picture and measure is period. So how we get from one to the other is standard frequency. So angular frequency is 2 pi times standard frequency. I'm sorry. Well, yes, that's true. But period is 1 over frequency. Angular frequency is 2 pi times regular frequency. Bottom line, like this is the question I was going to ask you. I'm just going to show you right now. I'm going to put this, I'm going to upload like these expanded notes in 1 minute when we're done. But like, so bottom line, if some oscillator has an angle, I'm just going to say this. I'm not going to quiz you, but we have like 30 seconds. Let me just say this to summarize. If you have some oscillator has an angular frequency of 6 pi radians per second, we would need that information so we could plug it in and take a cosine and make predictions. But what would that mean? If I say the omega is 6 pi radians per second, if I ask how many seconds does it take to complete a cycle, I can go in my head. I could say 6 pi radians per second. Oh, well, there's 2 pi radians in every cycle. So 6 pi radians per second, that means the thing is doing 3 cycles per second. And that means it takes 1/3 of a second to do each cycle, right? If I give you an angular frequency of 6 pi radians per second, you could tell me that the period is 1/3 seconds per cycle. Again, I'm going to upload these notes, so don't worry if I'm going a little fast now, but this is the whole deal. Like the angular frequency you need for the math. The period is what we can all relate to. And we all know we can't relate to angular frequency. That's why I'm explaining it. but it can be explained in terms of, so similar last example, it's 420. If an oscillator has a period of 4 seconds, so it's T, capital T is 4 seconds for one cycle, what would omega be? Well, if its period is 4 seconds per cycle, then its frequency would be 1/4 cycles per second, right? I.e. 1/4 hertz, right? And if its frequency is 1/4 cycles per second, that means if I multiply by 2 pi, it's doing pi over 2 radians per second. Where did I get that from? Because 2 pi radians would be a full cycle. So pi radians would be a half cycle. So pi over 2 radians would be 1/4 of a cycle per second. That's how it works. But she or he is absolutely right that like we wouldn't need all three, except that we do. Like you need omega for the math. But we all can't relate to omega. We can relate to T. So F is how you get back and forth between the two. Hopefully that made some sense or so. I mean, I'll ask you next time if that worked for anybody or not, but that's the deal for today. I'll hang out for, pi is infinite. Yes, that is true. Pi, and someone wrote pi is infinite. Yeah, well, pi does have an infinite decimal expansion. Yes, that's true. Okay, hopefully that helped sort of kind of just keep on doing what you're doing. I'll hang out for a second if there's any questions, but thank you so much. Yes, have a nice day. Have a good day.
Have a good day, Professor.
Good day. Oh, okay, wait. Okay. There's a question. Okay, I'm gonna stop the recording. Hold on. I see there's a question. Hang. Stopping the recording.